This is my PMC device, which stands for Portable Medicine Cooler. And what does it do? It cools medicine while trying to be portable. Yeah, I'm not really the best at naming things. Now, to the person or people who are about to drop a comment and say, it doesn't look so portable. To you, I say, it does. And why don't I challenge you to try my comeback to prove its size or something? But yeah, I know it doesn't look super portable, and that's because this was my first attempt at building anything self-designed for thermal isolation and cooling. In the end, my limited experience plus the inefficiency of Peltier coolers resulted in this spectacle of a machine. You may ask, why did I build this? And the answer is, as an engineer that's trying to change the world, I built this of course I just made a device that had some real world application, but what's even more important is that I just like to build cool stuff with tech that I have access to. I had come across these Peltier cooler modules and I really wanted to put them to use in a functional and beneficial manner. Some of you may ask, what is a Peltier module? And as a professional YouTuber who explains the things I do, in layman terms, a Peltier module is a solid state heat pump, and the slightly more technical definition is Peltier coolers, also known as thermoelectric coolers, TECs, are solid state devices that use the Peltier effect to create a temperature difference between two sides of a module by passing an electric current. So what could one do with such an intricate component, you may ask? Cooling. Yes, cooling, obviously. So I just thought of cooling things with it, but I needed it to have a function and be something useful too. After sifting around and seeing a design somewhere I can't even remember, I decided that I wanted to make a medicine cooler that could fit in your pockets. Well, look at the size of the beast of a portable device this is. Now, let's get into how I built this. Following my previous video where I talked about how to go from idea to prototype, the first thing I did was to list out all the features of the project, which in this case were the following. 1. You needed to be able to cool temperature sensitive medicine, and in this case I selected insulin as target because it's small, well known, and could potentially have a use case scenario, which meant I needed to reach temperatures as low as 2 to 8 degrees Celsius, which is needed to store unopened insulin. 2. I wanted an on-screen interface for the device which displays the temperature. 3. It had to be portable. 4. It must be battery powered and last a somewhat long transportation trip time span before needing to get plugged in. 5. It should have temperature control via a mobile app and a default temperature control setting. An easy set of requirements, right? Right? Well, I didn't know what I was getting myself into, and after going through all the different features, I jumped straight into research, and I was able to narrow down my methodology in order to have any chance of success. With the research, I came to the following findings. Peltiers are criminally inefficient, and that's why they don't just replace the conventional refrigeration systems that we have. They are power hungry, meaning that a 50-watt model will just constantly draw the same 50 watts of course, so long as they are powered, and because it's inefficient, it's not preferred. They also need heat sinks, emphasis on need. It's not a suggestion if you want to get really low temperatures, and that's because in order to get a much cooler side, you need a temperature difference between the hot side and the cold side, meaning the heat generated by the hot side, if not dissipated to the environment by a heatsink and fan, could flow in reverse and warm up the cool side, so active cooling is very much needed. I also looked at temperature control techniques, and I settled on a simple closed loop bang controller where there's a set temperature limit, a lower temperature and an upper temperature limit, which defines a set range. The Peltier cooler comes on, and then the temperature is measured using a temperature sensor for feedback. Once the chamber is cooled to the lower temperature limit, it goes off, and of course it starts to gain heat from the environment and temperature increases. Now that's obviously dependent on how thermally isolated your system is. Once the temperature has risen to the set upper limit, the Peltier cooler comes on again and starts to cool it down, and hence the bang controller setup. But before settling on the upper and lower limit temperature control, I explored PIE control and PWM control for the Peltier modules. But from every source I got, it just seemed that PWM control would just tank the efficiency even further, and that's not an option because efficiency is very important in this build, as it's a portable device running on batteries. If you like control engineering and projects like this, why not control your finger or cursor and tap that subscribe button, turn on post notifications for the next video, and I'll be exploring PID controllers for a robot, so stick around if you want to see more of that. With all the information I needed, I got to work on the electrical design the device would follow, hence the first prototype, and Here it is. The design consists of the Peltier cooler, which is accompanied by its cooling fan, a relay to switch on and off the Peltier cooler, an ESP32 microcontroller which reads temperature from the DHT11 temperature sensor, which I used instead of the original DS18B20 temperature sensor because it kept on getting faulty after a while. In the design, I had a custom battery pack made out of three 10,000 mAh LiPo batteries, all in series to get a 3S battery pack which connects to a 3S BMS board. The input is from a barrel jack, which is then passed through a buck converter that can provide constant current and constant voltage to charge the battery pack, which I did find on AliExpress. There's also a basic LM2596 buck converter, which provides lower 5 volts for the other components. I also added switches, indicator LEDs, and an OLED screen amongst other components in order to make a compact and fully functional design. The first thing I did after getting the materials I bought was to test the Peltier cooler setup I had gotten from AliExpress, which had 2 cooling fans and a huge heatsink. After powering it on, within a couple of seconds you can see condensation taking place and water droplets already forming. Here I tried using the DS18B20 temperature sensor to check the temperature of the cold side of the Peltier cooler setup. In a spur of self-induced ideas, I guess, I decided to cut off the fins of the heatsink on the cooling side in order to have more access to a wider panel for the cooling side, and because I needed an overall much flatter setup for a compact device which I planned to build. Well, that was the aim of the device, to be much more compact than bulky. After using a cloth to cover the cold side, with the temperature sensor on it, I was able to get lower temperature readings to the lower limits of under 7 degrees Celsius, also sometimes reaching 5 degrees Celsius. And with that done, I knew I was going to be able to get the lower temperatures that I needed from this setup. Next thing I knew I needed to do was to build a thermally isolated chamber to prevent heat gain after cooling was done. After doing some cutting and measuring, I was able to make this styrofoam chamber because it was the best insulation material I had at hand and I could use to craft a chamber quite quickly. After failing to succeed with that first setup, I tried to make an all-metal casing enclosed in styrofoam to enable a wider surface area to cool, but that just didn't work as well as I thought it would. So the next thing I thought of doing was to make a gasket and to put the smaller cooling fan back on in order to improve air circulation. Since the smaller surface area was getting cold air really quick, why not circulate that cold air and have it cool the warmer air? I first of all made this makeshift gasket as a random idea out of scraps of a Vero board I had used much earlier, and then moved on to 3D printing the gasket. And while I did that, I remade the chamber and wrapped it in insulation tape for the next test. Now this was just me winging all this to see what the possible results would be like, and I think I had some good success with the setup to some point, so I redesigned the gasket again to have a slot for the cooling fan, and here you can see the new gasket with the fan holder and the rest of the setup all coming together nicely. I also tried 3D printing a chamber out of PLA, but that didn't go too well for reaching the much lower temperatures I needed, and because of my print settings and a bunch of other factors, I just didn't want to try doing this again and again and again since I wasn't sure I was going to get the results I wanted. In order to get a powerful enough battery pack, I bought and took apart a 40,000 mAh power bank where I got 3 of its 4 cells and coupled it into a battery pack using the 3S BMS, as it was the only way I could think of dreaming to get the capacity I needed with the price point of my budget. With the chamber setup, battery pack situation sorted out, and cooling setup all ready to go, I started to assemble all the electronics and components into one great pile of wires and a hand soldered circuit board. Here is a montage of my suffering. At this point, I had rigged the setup to measure temperature and humidity in the chamber, changing from the previous sensor to the DHT11 temperature sensor. I added the indicator LEDs for the device, one for telling that the device was powered on and the other for indicating charging. I also wrote the code to connect to the IoT app called Blink, which allowed me to have a good interface for the web and Android part of the setup. Here's a full restart test to show how the device, even as a pile of wires and circuit board, worked. With the device working and getting results, I was marginally okay with it. I went on to 3D model the casing for all the electronics. In this model, it's separated into three main sections: the cooling section, the isolated chamber, and then the electronic section. Now let me have a rant. This was just me maybe a month or two into 3D printing, so I was still inexperienced. But living in a country with no constant power supply, where they bring and take the power like they're playing a game of whack-a-mole, it makes 3D printing anything longer than 20 minutes a mind-torturing game of deciding when to start the print, hoping that the guys at the power session don't play with your hopes and dreams that day. And of course, a UPS would help. The one I got locally was trash and it spoiled after some use. The main solution would be to run a generator during the whole duration of the print and to reduce the print time as much as possible. And so I did my best. And unfortunately for me, just inconveniently enough, my printer started having issues. I didn't know until much later after this project, but my cooling fan had chipped on one of the blades, causing it to operate at varying speeds with a lot of noise and instability, which caused an insane amount of clogging due to varying cooling speeds. This caused me so much stress that I don't even wish to remember the trauma. But yes, after the project, I was able to get a replacement fan, and I haven't had this issue with prints failing since this period, because prior to this, I had prints fails on the first layer and maybe about an hour or 2 hours into the print. One thing you might notice is that other than the first part, everything else was a failed print. Every time a print made significant progress but failed, I measured the height, went into the card design, cut it from there, and sliced what was left for another print with the aim of gluing it all together. I couldn't afford to waste filament nor time as I was already too frustrated. After using a ton of super glue, hot glue, 2-part acrylic glue, and my hopes and dreams, I was able to finally assemble the entire case. The plan is to obviously upgrade the printer, power supply setup, and a lot of equipment, so if you want to stick around and make that possible, subscribe, leave a like, and share so we can grow and get there someday. With the case assembled, what I did next was to put all the electronics into the casing, which was a battle of wires in itself, but all I had to do after doing that was to cover the cases and put the screws on. And if you notice, I made the chamber a snap fit case for ease of accessibility with a certain degree of rigidity to create a tightly sealed chamber for storing medication. Here's the final result and setup test run of the project. Now, unfortunately, the OLED screen kept on glitching out like crazy and seemed to be faulty, but at this point, I was done. I was able to have a fully working system that had both an offline and online mode. This is the full sequence of operation for how it works. Once it's powered on, it checks if the Wi-Fi access point is available with the programmed SSID and password, and if not, it switches to the offline mode, maintaining a pre-programmed temperature range of between 6 to 10 degrees. But if it successfully connects to the internet, the temperature range can be set on the mobile and web app hosted on the Blink platform. The on-device screen and app interface show the temperature of the chamber, humidity, and battery level too. Editor me here, and I think I made a mistake with the voltage range of the code that shows the battery percentage, but oh well, it is what it is, I guess. And there it is, my very own portable medicine cooler. And as for the results, I was able to get a battery runtime above 1 hour 30 minutes, sometimes reaching above 2 hours, and with temperatures in the chamber constantly reaching below 13 degrees Celsius on most tests, with the best performance reaching temperatures between 8 to 10 degrees in the chamber. In conclusion, it's obviously a bulky build for what I set out to make. I couldn't really get those sub 5 degree temperatures in the chamber, and it obviously was not thermally isolated enough. But if you enjoyed watching and making it this far into the video, make sure to subscribe, drop a comment if you want me to revisit this particular build, and leave a like. It actually helps us do more. It's left for you to judge whether this was a success or a failure, but I take it as a successful failure. May the engineering forces be with you, and see you on the next video.